I'm about to show you a space weapon plan so wild it reads like sci-fi. A $175 billion dome meant to stop missiles from space. I wish I were kidding. In this video, you'll see the tech, the timelines, the price tag, and also how and why this could change everything. Could Elon Musk really build a $175 billion smart space dome? Think of the name as a promise: detect, track, and stop threats before they hit. The idea in the public debate is one integrated network, space sensors, AI decision layers, and interceptors all working together. The Golden Dome missile defense system is a proposed shield designed to detect, track, and shoot down virtually any threat from the air before it hits American soil. That shows the exact promise: one system to cover boosts, mid-course, and terminal phases. The real question is engineering scale, satellites, low latency links, interceptors everywhere, and whether a private actor could lead or only partner in that build. What almost never gets discussed is command and control. Detecting a missile is one thing, deciding whether to shoot is another. In a real crisis, that decision may need to happen in seconds. That means AI-assisted battle management systems filtering sensor data, removing false positives, and recommending intercept solutions instantly. But here's the danger: automation in nuclear-adjacent scenarios raises escalation risks. If software misidentifies a launch or glitches under cyber attack, the consequences are historic. So any smart dome would require not just satellites and interceptors, but hardened cyber defenses, redundant human oversight layers, and strict engagement protocols. The smart part isn't just hardware, it's decision architecture. Why are experts saying, let's pretend it's 2030? What does that reveal? The scenario people use shows where the system must work: multiple launches, hypersonics, complex trajectories. Let's pretend for just a moment that the year is 2030. That short setup is literally a stress test. If threats can come from hypersonics to FOBS, fractional orbital weapons, the system must detect and react in milliseconds. For anyone imagining a Musk-led dome, this clip is why private rocket and satellite capability matters. Launch cadence, manufacture, and networked sensors are the backbone of success. How will sensors and satellites actually track missiles in real time? This is where the plan leans on hundreds, maybe thousands of space sensors. The only time that we can think of in the history of the United States where we have gone after something this complex was the Manhattan Project. The comparison to Manhattan highlights scale. You need a persistent global infrared and tracking layer, not a single satellite, but constellations in polar and equatorial orbits feeding AI that can keep custody of every maneuvering object. Practically, that means huge investments in sensor manufacture, bandwidth, and secure low latency links, the kind of things both startups and legacy primes can supply, but only at scale. And scale changes physics into economics. Thousands of satellites mean constant replenishment because low Earth orbit assets degrade from radiation and atmospheric drag. That creates a permanent launch and replace cycle. It also means supply chain stress, rare earth materials, radiation-hardened chips, propulsion units, and secure optical links. If even one part of that chain bottlenecks, the entire constellation weakens. A smart dome would therefore double as a national industrial mobilization effort, reshaping semiconductor policy, launch infrastructure, and space manufacturing for decades. Do the current interceptors, Aegis, THAAD, Patriot already do this job? We already have strong building blocks, but they cover pieces, not the whole. Aegis has been proven in real-world tests. In 2024 on Guam, where it successfully engaged a medium-range ballistic missile with the SM-3 Block 2A variant. Those systems are excellent at mid-course/terminal phases, and companies like Lockheed Martin are central to scaling interceptors. But boost phase intercept, the Holy Grail, demands space-based interceptors or directed energy, which we do not yet field at scale. So current systems buy time and add layers, but they do not eliminate the need for a huge sensor/interceptor constellation. There's also the saturation problem. Even the best interceptors can be overwhelmed if dozens of missiles launch simultaneously. Adversaries know this. Missile defense is often described as a numbers game. Can the defense afford enough interceptors to handle worst-case salvos? If interceptors cost millions each and attackers build cheaper offensive missiles, the economics tilt toward offense. That imbalance is why layered detection and boost phase interception matter so much. Stopping one rocket early prevents multiple warheads later. Who set the $175 billion price, and can the timeline be trusted? The price figure entered the public debate as a political target. President Trump has said the Golden Dome will cost $175 billion and be done by the end of his term. $175 billion is a headline number. Experts estimate life cycle costs far higher once you include replacements, upgrades, and sustainment. Congressional Budget Office style estimates push the long-term bill into the hundreds of billions to nearly $1 trillion across decades. Timelines are optimistic too. Satellite constellations, manufacturing scale-up, and weapons testing rarely move at campaign pledge speed. Will industry really ramp up production, and who benefits? If this becomes policy, primes and space firms will scale fast. Lockheed Martin is significantly expanding production of its Terminal High Altitude Area Defense System, better known as THAAD. Firms already betting on contracts, new factories, and IPO moves from space startups trying to capture the sensor and bus market. Expect private manufacturers to be major suppliers, which is why a figure like $175 billion becomes both a defense plan and an industrial policy. Is boost phase interception the real game changer? If this dome is ever called smart, it will be because of one thing: stopping a missile in the first few minutes after launch. That is the boost phase, when the rocket is still burning, glowing hot, moving slower than it will later, and before it releases multiple warheads or decoys. Boost phase intercept is considered the holy grail of missile defense for one reason: it's the only time when the missile is moving relatively slowly. If you hit it there, one shot can stop everything inside it. No decoys spreading, no maneuvering warheads splitting apart. But here's the catch: you need satellites already overhead with interceptors ready to fire within seconds. That means a dense constellation in low Earth orbit, hundreds, maybe thousands, and that's where the scale explodes. A private launch company could dramatically lower launch costs, but the engineering challenge isn't just rockets. It's guidance, targeting, global networking, and resilience against attack. How dangerous are hypersonic glide weapons really? Traditional ICBMs follow predictable arcs. Hypersonics don't play by those rules. Another newer threat is the boosted hypersonic glide weapon, greater than Mach 5. After they enter the atmosphere, they maneuver to their targets on a glide vehicle. They glide low, they change course mid-flight. Radar coverage designed for high-arc missiles struggles to track them consistently. This is why sensor layers in space become critical. Ground radar alone isn't enough. You need infrared detection from orbit, plus tracking satellites that can maintain custody even when the weapon zigzags. Without that, the smart and smart dome disappears instantly. What about fractional orbital bombardment systems? Now let's talk about FOBS. These are designed to avoid predictable arcs entirely. This kind of weapon is launched into a partial or fractional orbit. It can approach from unexpected angles. Why older defense concepts struggle? If a weapon can come over the South Pole instead of the North, or stay low enough to reduce radar warning time, then early detection must happen in orbit. A smart space dome must provide 360-degree planetary coverage, no blind zones, no gaps. That requires layered satellites and multiple orbital planes. And maintaining that coverage year after year is expensive because satellites in low orbit degrade and must be replaced. Will space interceptors spark an arms race? This is where the controversy explodes. The moment you put interceptors in orbit, other nations see them not just as defensive tools, but potential offensive weapons. If you put interceptors in space, you could potentially do a lot more than just take out missile threats. This is why China and Russia publicly objected. They argue it militarizes space further, and then you get responses like this. It will exacerbate the risk of turning outer space into a battlefield and starting an arms race. Those words are not exaggerations. Anti-satellite weapons already exist. Russia destroyed one of its own satellites in 2021, creating debris. China has tested anti-satellite missiles, so if a smart dome relies heavily on space infrastructure, it must also defend that infrastructure. Hardened satellites, redundant networks, rapid replacement launches. Otherwise, the entire shield could be blinded before it fires a single interceptor. Is $175 billion even realistic? The headline number grabs attention, but listen closely to this financial reality. The real lifetime cost could be far higher. Congressional projections have floated ranges between $500 billion and nearly $900 billion over decades when sustainment is included. Remember, satellites must be replaced, interceptors expire, software needs constant updates, AI systems must evolve against new countermeasures. A smart dome is not a one-time purchase. It is a permanent national infrastructure commitment that's closer to maintaining a digital electric grid in space than buying a weapon system. And here's another crucial reminder. The Golden Dome is the most ambitious missile defense plan ever, and potentially the most ambitious defense plan, period. Ambition at that level means technological spin-offs are inevitable, even if the original vision evolves or scales down. Historically, massive defense projects spill into civilian tech. The Manhattan Project accelerated nuclear energy research. The Apollo program pushed microelectronics and computing. A smart space dome could accelerate space-based solar power research, high-bandwidth laser communications, autonomous satellite servicing, and advanced AI fusion systems. Even critics admit that when governments fund frontier engineering at this scale, secondary industries evolve around it. Could private space companies accelerate it? Now think bigger. A dense sensor constellation demands rapid, repeatable launches. That is where commercial launch capability becomes critical. Space infrastructure firms are already positioning themselves. Investor interest has been driven by the company's positioning in the space and defense sector, including its potential role in President Donald Trump's Golden Dome missile defense initiative. Wall Street is paying attention. Companies tied to satellite buses, sensors, and manufacturing automation all see opportunity. And if launch costs continue dropping, deploying hundreds of satellites becomes financially less impossible than it sounded a decade ago. The private sector cannot replace military command structures, but it can provide the hardware backbone. Here is another industry signal. Lockheed Martin is significantly expanding production, with annual output expected to grow from under 100 today to as many as 400 per year. Scaling interceptor production fourfold is not theoretical. It is already happening. That suggests policymakers are preparing for higher missile defense demand regardless of final program branding. So can any shield ever be truly impenetrable? Even supporters admit this. Can any shield really be impenetrable? It can't. No system guarantees perfection. Missile defense is about reducing risk, increasing deterrence, and complicating an adversary's plans. A smart space dome would likely work as a layered defense, boost intercept if possible, mid-course if needed, and terminal as a last line. It is redundancy that creates strength. But redundancy costs money. It invites countermeasures. It fuels competition. It pushes AI integration into military decision cycles faster than ever before, and it shifts warfare further into orbit. This isn't science fiction anymore. It's engineering, politics, money, and survival. The real question isn't whether America builds a dome, it's how smart and how sustainable it actually becomes. If you want deep, no-hype breakdowns of the tech shaping our future, from space weapons to AI warfare, hit subscribe and stay ahead of the curve.